We already talked about measure of central tendency like mean, median and mode, which are different ways that we measure the middle or the center of the dataset. Also in the last video we have learned that what is range and interquartile range, which are the part of measurement of dispersion. In this video we will cover standard deviation and variance, which are also the part of dispersion and help us to calculate the measurement of spread. So before discussing mean variance and standard deviation, we should first understand the difference between population and a sample. In statistics, when we refer to population, we are talking about the complete group of all the individuals or subjects. However, it is not always feasible or desirable to study every single person in the population. In such a case, we select a smaller group from the population and call it a sample. We hope that this sample will accurately represent the population as a whole. So by studying a small portion of subjects, we can gain insight into the population. So let us consider an example. Suppose we have a region with the population of 10 million. To study this population, we can collect data from a sample of 1 million people. By making inferences based on the data we gathered from this sample, we can estimate the characteristics of the entire population. For instance, we can measure the height of all 1 million people in our sample, calculate the mean height, and then assume that the average height of the population is similar to that of our sample. However, to ensure that our sample is representative of the population, we must be careful in selecting the sample to avoid any biases. It is crucial to determine whether we are working with a population or a sample when dealing with the mean variance and standard deviation. This is because the formula used to calculate them differ depending on the type of data. So let us go ahead and make a chart. Here we refer to the total number of subjects in population. We use the capital letter N. Therefore, if you come across the letter N, it indicates that you are dealing with a population. Essentially, we will examine every single person, object or subject in our population. When we take a sample from a population, we denote the sample size as lowercase n. The formula for calculating the mean of a population and a sample is the same, except for the use of capital letter N for population and lowercase n for sample. When calculating the mean for a population, both ends of the formula are represented by capital letter N. However, when calculating the mean for a sample, we use x bar instead of mu to represent the mean of the sample. The formula remains the same except that we use lowercase n instead of capital N. So the numerator has the lowercase n and the denominator as well has lowercase n. So on our way to going through variance and standard deviation, let's work through an example using the formula we already have for mean. So let us take an example where we have 18 data points representing the population. We can represent the number of data points as n, which in this case is equal to 18. If we want to find the mean, we can add up all the scores and get a total of 326. Since we have 18 data points, we can divide this total by 18 to get the mean. So our mean is 18.11, which will be similar to both population and sample. So what about variance? Variance is measure of how spread out our data is around the mean. The formula for population variance is x sub I minus mu. To understand this formula, we need to remember that x sub I represents any single data point in our dataset. For instance, let's say we have a set of data. To calculate the deviation of each point from the mean, we can start by taking the first value of the data and plugging it into a formula x sub I. We then repeat the process with the second value of x sub I and so on until we have gone through all the data points. Essentially, we are substituting each data point into the formula, then subtracting the mean we previously calculated, that is mu, from it. Basically, what we are doing is calculating the difference between each data point and the mean. So for instance, if we consider the smallest value, that is 10, and subtract it from the mean 18.11, the result will be negative 8.11. Similarly, if we take the largest value in our data set, that is 29, and we subtract the mean, that is 18.11, so we get a value positive 10.88. So what that tells us is that 10 is below the mean because it has a negative answer and 29 is above the mean since it is a positive. In either case, we are simply moving further away from the average or the mean. In the variance formula, we calculate the difference between each data point and the mean. We then square the difference, which will always result in a positive value. So when we square the distance, the result is an area. So let me demonstrate this. So when we measure a distance of 10.88 units, we simply state it as 10.88 units. However, if we square this distance, we are essentially creating a square with sides measuring 10.88 each units. So this results in an area being calculated instead of a distance. So let me just clear this out. So this expression x minus mu squared represents a portion of the area and not the distance. So in the variance formula, we square the values because it gives more weight to the outlier data. This means that data points that are farther away from the mean will create a bigger square. Later on in this playlist, we will learn why this is helpful. We want to minimize the size of all the squares as each point creates a square of a different size. So by minimizing the size of the square, we can minimize the variance. To calculate the variance, we first square the distance to get an area. For each data point, we then add up all these areas together, and finally we divide it by the number of data points denoted by the capital letter N for our population. So this gives us the variance, which we represent as a sigma squared. So it is worth noting that we call it sigma squared instead of sigma because the standard deviation is just the square root of the variance, and we want to keep the standard deviation represented as just a sigma. So the formula for sample variance is similar to that of the population. However, instead of using the sigma squared for the population, we use S squared for the sample. So this is defined as the sum from the first term to the last term in the sample, represented by the lowercase n. We still use x or y, but now we subtract it with the mean of the sample represented by the x bar, instead of the mean of the population represented by the mu. We then square the results and divide it by the number of subjects in the sample, represented by the lowercase n instead of the capital letter N. When calculating the variance for a sample, we divide the sum of squared deviation by n minus 1 instead of n. The reason for dividing by n minus 1 instead of n is because when we calculate the variance using a sample, we are using the sample mean, which is an estimate of the population mean. Because the sample mean is an estimate, it has some degree of uncertainty. Statisticians found that by dividing n minus 1 instead of n corrects this uncertainty, giving us a more accurate estimate of the population variance. So this correction is called Basel's correction. So now we do the same thing as we did in the population calculation, but instead of dividing it by 18, we will divide it by 17, that is n minus 1. And we get the variance for the sample, that is approximately 31.86. So when a value is squared, the square root of that value will cancel out the exponents. Therefore, the standard deviation can be represented by the sigma. When a value is squared, the square root of that value will cancel out the exponents. Therefore, the standard deviation can be represented by just a sigma. So after computing the standard deviation for population, we can calculate the sample standard deviation by taking the square root of the sum of x squared, which is equivalent to the capital letter S. So when we take the square root of 30.098, we get a standard deviation for our population, that is 5.49 approximately, which if we round to the nearest 100. And for the sample, we have standard deviation of approximately 5.64. So this was it for the variance and standard deviation, and in previous video we have covered range and interquartile range. So that's wrap up measurement of dispersion. Hope you have liked this video. Please subscribe to my channel and I will see you in the next video.